Okay, we're finishing up chapter 5. Let's go. Section J is about cubics, which are going to generally increase from left to right if their leading coefficient is positive, and generally decrease from left to right if their leading coefficient is negative. All of the other function transformations that we've studied before still apply here. So if our A value here is getting larger, then the graph is going to become steeper because that's a vertical stretch. We could also move a cubic around in the plane by giving it a horizontal translation and a vertical translation, written either inside the function or described as a vector. The rules we see here really apply to any odd-powered polynomial. So you can think about lines. That's a x to the power of 1. They're going to go up from left to right when it's a positive x term, and they're going to go down from left to right when it's a negative x term. And the same thing is going to be true for fifth degree polynomials, seventh degree polynomials, and so on. The only thing that really changes about their shape is how many little bends they have. So a fifth degree polynomial might be something like that, and then a seventh might be something like that. In general, the maximum number of turning points that a polynomial graph has will be one less than the polynomial's degree. So a quadratic has degree 2, and that could only have one turning point. A cubic is degree 3. It could have 2 turning points, although it could also just get flattened out, which is kind of what it looks like here. Our fifth degree polynomial could have up to 1, 2, 3, 4 turning points, and so on. We'll be able to work out exactly where those turning points are, and we'll also be able to work out where a point of inflection is. A point of inflection means it's basically where the graph starts to bend or curve in the opposite direction. So I've drawn one in right here. To the left of it, the graph is kind of curving in a clockwise direction, and then all of a sudden it's curving in a counterclockwise direction. So we'll be able to identify where those and where the turning points are once we know calculus. For now, we're just going to do some simpler stuff. As you'll see here, it's just going to be pretty basic algebra and function transformations. So for example, here you should be able to picture what the graph of x cubed looks like. It's going to be the dotted graph right there. And I know I'm kind of giving away the answer here, but this other one, it's the same graph. It's just been shifted over, right? 2 units to the right and then 1 unit down. All right, so here's all the stuff we got to know. So like I said, when our A value is positive, our cubic will have one of these two shapes. So it's either turning twice or it's just flattening out, and then going downwards if A is negative. Every cubic has to cut the x-axis at least one time. It might be 2 if the x-axis touches on one of those turning points, or it might be 3. If we can factor the cubic into 3 linear factors, then it's going to have 3 separate zeros. If we can factor it into a quadratic, well, a repeated linear factor, and then a single one, then we're going to have that single linear factor will correspond to a root where we cut the axis, and the repeated one is going to correspond to a root where the graph kind of bounces off the axis, or they say it touches the axis. We don't really use this terminology, at least in this textbook series, but you may have heard that the x minus alpha factor has multiplicity 2. And anytime that we have an even multiplicity, which really just means that the factor is repeated an even number of times, we will always see the graph touch the x-axis there as opposed to cutting it, which is what will occur when we have a multiplicity that's odd. So here we have just a single linear factor repeated 3 times, so that's odd multiplicity, and we go through the x-axis at that point. It is possible, of course, to have turning points, but only have 1, 0, and that's if the quadratic factor doesn't have any real roots itself. So if the discriminant of that quadratic is negative, then we're only going to have an x-intercept at alpha. With all that in mind, we should be able to get some good sketches down of cubic functions where we identify all of the zeros, so that's all the x-intercepts. We should also be able to get the y-intercept as well. So here's that first one. I know it's going to cross the x-axis at -3, +1, and +3. We know that the leading coefficient is positive, which means it's going to have a shape that's going up as we move to the right. And then we just substitute in x equals 0 to figure out the y-intercept. Easy. And this other one, same idea. It's only going to have 2 x-intercepts this time. They'll be -1/2 and +2. It's going to have a negative leading coefficient. We see there, so it's going down from left to right. Again, we find the y-intercept. Okay. We can also work backwards. If we're given a picture of a cubic, we should be able to work out what the equation was. This one's going to have 3 roots, so I start off by considering the linear factors, x plus 1, x minus 2, x minus 4, and then we need to use the fact that we have a y-intercept of -8 to figure out what constant we should multiply by. From the shape, we know that constant a here, it's got to be negative something, but again, we just put in x equals 0 into these factors, and then we figure out, oh, well, when x is 0, it has to equal -8, and then we can identify what a is. We're going to do the same thing over here, although I would do it slightly differently than the book does. Again, we have a single linear factor here, and this one's going to be repeated. They're going to write those down as x plus 3, which I agree with, and they use 3x minus 2, and that works. I mean, that's clearly going to get you the root of 2/3. And then again, they put in 0 for x's, set it equal to 6, as that is the y-intercept, to figure out what the a value is. I would have considered that as x minus 2/3 squared, then solved for my a. My a would have been 9/2. This function is the exact same thing as that one. You could think about taking that 9, splitting up into 3 and 3, and then distributing rather a 3 into each of those repeated terms, and that's how you're going to get 3x minus 2 squared. But whatever makes you happy, people. All right, we should be able to interpret word problems as well. This is an equation that cuts the x-axis at 2 and -3. That means it's going to go through the x-axis at both 2 and -3. Now, we know for a cubic, if it's cutting the x-axis at 2 points, that actually means it's going to have to cut it at a third point as well. So our 2 linear factors we'll start off with will just be x minus 2 and x plus 3, both to the first power. Then we're given its y-axis intercept and some other point, so we can do some work with that. So we've got our 2 linear factors that we know, and then there's a mystery linear factor. And you could write it as ax plus b, or you could write it as just x plus b, and then take the a kind of out in front. Since we have 2 unknowns, we're going to make 2 equations. One is going to use the y-intercept. One is going to use the point 1, -40, and from there we can work out what a and b are. Section K is going to be the same stuff. We're just talking about quartic functions now, so degree of 4. So just like a quadratic, when our leading coefficient is positive, the graph's going to open upwards, kind of like this one we see here. If the leading coefficient was negative, the graph would open downwards. Just like with cubics, what we know about, well, just like with quadratics as well, I suppose, what we know about the x-intercepts will tell us information about the linear factors and whether they are repeated or not. So if we have a quartic that looks like this, that means that it's going to have 4 separate linear factors, one for each of these x-intercepts. Something like this picture here is going to have a single factor here, a single factor here, but right there, that one's going to be repeated twice. Same thing over here. That one single root is repeated twice. Those 2 are singular. If we see something like this where it gets flat and cuts through the x-axis, just like with a cubic, when that happened, that means that we're going to have a linear factor that's been cubed, and then this one where it goes kind of straight through is going to be a separate linear factor that's just the power of 1. And it is possible that we could have a single linear factor that is repeated 4 times. That's going to give us a very flat bottom. It kind of looks like a parabola, but it's really flat down here. All right, so you should be able to tell, kind of by looking at the shape of these things, what the basic factorization of the quartic should look like, whether it should have terms repeated once, twice, 3 times, or 4 times. But of course, it's not as easy as just counting the number of times we cross the x-axis, because we see here 1, 2, 3, and 4, and there might even be less than that. Okay, so it's possible, just like with our cubics, that we might factor the quartic, into, say, in this case over here, this would have 2 linear factors where we're cutting the x-axis, but then the remaining quadratic factor might not have any real solutions. So that's how we would get this shape here above the x-axis. And it might also be possible to factor the quartic into two quadratics, neither of which has any real solutions. And so that would give us a quartic that is, in this case, positive definite. Now again, we'll be able to work out all sorts of information about this stuff once we know some calculus. Right now we're just kind of thinking about x-intercepts and how that relates to the equation of the graph. So again, just like before, we should be able to sketch graphs just based on looking at the linear factors. So there's your answers. It's the same thought process as what we had with cubics, so I won't talk about it. Here's another one where we've got the picture. Can we build the equation by working backwards? Yes, I certainly hope so. We can do word problems. Again, same as before. And notice here, we've got it touching the x-axis at 2. So that means there's going to be a multiplicity of an even power there. But since we also know that it's cutting the x-axis at another point, then since this is a quartic that we're discussing, then that means that x minus 2 has to be just to the second power. Couldn't be to the fourth. And we do that the same way as we did before. We solve a system of equations, and we're done. And that's really all there is in sections J and K. It's unlikely that you'll have to work with higher degree polynomial graphs, at least without the aid of a calculator in this course. But in the event that something does show up, just think about what you know about cubics and quartics, because the ideas here can be extended to really any degree polynomial. And you can play around with stuff. You can make up your own polynomial. Here's an 8th degree one. Is it behaving the way that we expect it to? Well, kind of. I mean, here I've got a 0 at -3. It's getting kind of flat, but going through it. That's what we're getting here from this term, which is multiplicity 5. Odd power going through. Over here, we've got -7. It looks like the function's actually just coming down here and stopping at the x-axis, but actually what's happening is it is bouncing off. My scale is just not helpful to see that. So it's coming down and then going back up again, and that's exactly what we expect here from this repeated linear term here. And then, of course, we have a single root at +2. And here's the same graph, just at a different window. So the x-intercepts are a little bit harder to spot, but we can certainly see the general shape of it. It is going up, which matches what we would expect from an 8th degree polynomial. And before we move on, I just want to remind you about the fundamental theorem of algebra from the previous video. It told us that the degree of the polynomial must match the number of complex roots that it has. So these are all 4th degree polynomials. They got to have 4 roots. Here's 1, here's 2, and this one counts for 3 and 4 because it's a repeated root, right? There's 2 roots there. Something like this one here has 1, 2, 3, 4. In those 2 examples, all of the roots happen to be real numbers. That's not always going to be the case. For example, this one has 2 real roots, and then the other 2 are going to come as conjugate pairs. And this one over here, there are no real roots. All 4 of them are going to be complex, and they're going to come in 2 separate conjugate pairs. Okay, so section L is all about paper 2 questions. So we've got a calculator, and we're going to use it just a little bit to give us a little hint, and then we're going to do the rest of our work without a calculator. So this is when we're trying to find exact zeros of complicated cubics or quartics. So let's take a look at one. So we want to find the exact zeros of this thing. Now chances are you don't know how to factor a cubic, and that's okay. You shouldn't know how to factor a cubic. But if you're interested, go crazy. So there's no common factor for us to pull out here. The only thing that we can do is cheat a little bit. So we're going to graph this thing, and we're going to find out where one of the x-intercepts is. Specifically, we're going to find the nice x-intercept. And it'll be obvious which one is the nice one. It's going to have some sort of a decimal. Well, maybe it'll be an integer. If not, it'll be some sort of a decimal that we can work with. So in this case, our graph, which we'll see here, and just ignore the words that are come right there, our graph is going to clearly have an x-intercept of 0.666667, which we know is 2/3. So now we've got a linear factor of 3x minus 2. So this cubic is going to be equal to that linear factor times some quadratic. We know it's got to be 1x squared if we're going to get 3x cubed. We know it's got to end in a -1 if we want to multiply by that constant to get +2. So we just need to figure out what the coefficient of x is. We can distribute through, and we're going to get 3a minus 2 is going to be the coefficient of x squared here, but over here it's got to be equal to -14, so we can figure out what that a is. From there, we can then find the two exact roots of that quadratic, and we're going to do that by hand. So we use the quadratic formula on this, and we get 2 plus or minus √5, because the calculator is just going to give you two awful decimals for that. You'll have no way of figuring out what they are as an exact number. So this is the technique that we'll use to do that. Now, I don't think you should ever see a question like this on paper 1, but in the event that you did, just try substituting in some really simple values for x up here until you get 0 out. So like I would try x equals 1, x equals -1, maybe a couple of other integers. You shouldn't have to be guessing and checking to get a fraction like 2/3. That's ridiculous. But I really think if this shows up, it'll probably be on paper 2. If you'd care to practice another one, here it is. If you'd care to just see the answer, here it is. So again, we graph it. We find this decimal here. We've got to be able to convert that into a fraction. It's -1/6. That gives us a linear factor. We've got a quadratic we need to work out. We've solved that. It ends up having two complex roots. And by the way, for both of these examples, you could do it the way that I referenced earlier in the video. Like, for example, here, you could have made this linear factor x plus 1/6, and then you would have just had some a value, which you could have absorbed into your quadratic. You'll still get the same answer either way. Follow your heart. You should be fine. Now, this topic really should stop at cubics. We really shouldn't have to deal with quartics. I mean, you could do a quartic the same way, or even a higher degree polynomial. You would just have to find more roots in the graph that are obvious. So maybe there's a quartic, and two of the roots are easy fractions to work out, and then that'll give you two linear factors, and you'll still have a quadratic left over, so you can do the same thing as we did here. The final section is going to be about inequalities, which we kind of talked about back in the blue book, but now we're going to just discuss cubic inequalities really quickly. We're doing them the same way. If we're doing this by hand, we want to bring everything to one side of the inequality and then factor it and then draw a sign diagram. But if we do have a calculator handy, then we absolutely want to use that and just graph the whatever we're looking at, and we'll get an answer from there pretty quickly. So here's an inequality. Notice it does say solve exactly, so we're expected probably not to use technology for this, or at least we're not going to use technology just to get some decimals, although you'll see we actually are going to have to use the cheating method we just saw. So we bring everything over to one side, and we need to find the factors of this, which we don't know how to do, so we graph just that function, and then we find, oh, you know what? It has -2 as a root. Now this is an example of one that like maybe this is going to show up on a paper 1, and you're expected to just guess a couple of small integer values, and then you come up with -2 as a root. Great. Anyway, from there we get the second quadratic, and we're going to find out its zeros, which end up being 3 plus or minus √6. So now we got three special values corresponding to our three zeros. I mean, you can kind of look at the graph here since we have it at this point, or we can go through with the full sign diagram. We're going to see that we've got negative values to the left of -2 and in between those two irrational roots. So that means that our inequality is satisfied in those places. Had you just graphed this thing from the very beginning, just exactly as it appeared in the original, we have the cubic kind of in red and the quadratic kind of in blue. I don't know, I'm colorblind. The difficulty with this is you'd have to change your window to make sure that you could see that they cross over again up here. If your window on the calculator was originally just something like this, you might be tempted to think that they only intersect twice. Now, that doesn't make a ton of sense because a cubic function should grow more steeply than a quadratic does due to that exponent being larger. We'll talk more about that later on once we know some more calculus as well. But I don't know, just in general, you want to be careful if you're just trying to graph stuff because things might be happening off screen. I also think if you're going to graph things, it's often easier to graph not the original, but I think it's usually easier to graph the the second line once we've moved everything over to the one side, because then we know this is a cubic and we kind of know its general shape. And I don't know, for me, it just makes it easier to see what's happening on the calculator than when I have to concentrate on both a cubic and a quadratic at the same time.